Hello, I am Swati Verma, Assistant Professor, Chhattisgarh Swami Vivekanand Technical University, Bhilai. I welcome you all to the course on Industrial Automation and Drive. Today we will begin with our 10th lecture, continue with our 9th lecture, which covers PLC fundamentals, means Programming Logical Controller Fundamentals. Heading is PLC Fundamental 2. So let's start with the Central Processing Unit CPU. The Central Processing Unit CPU is the core of PLC, the Programmable Logic Controller, with the microprocessor serving as the heart of the CPU. While the terms Central Processing Unit and the microprocessor are often used interchangeably, but the microprocessor is specifically or mainly designed for the integrated circuit used by the Programmable Logic Controller PLC, and the CPU includes the additional components and circuits which are very necessary for the PLC operation. The Central Processing Unit CPU architecture encompasses digital circuits for data storage and recall, as well as circuits for communication with the programming unit. An executable program which are stored in ROM called as read-only memory controls the microprocessor. This executable program written in assembly language directs the microprocessor to perform the processing, the control internal units and handle the communication task. Here in the figure you can see the operational interconnection between a CPU and with the other units of a Programmable Logic Controller PLC. The Central Processing Unit of a typical PLC performs several fundamental operations like input-output operations, which involves communicating with the external world, scanning the inputs and updating the outputs. The logical and the arithmetic operations include the Boolean algebra functions like AND operation, OR operation, etc., and also the basic arithmetic tasks which include addition, subtraction, multiplication, etc., along with very specific operations like timing, counting and comparison. The reading, writing and spatial handling operations manages the memory content, whether it is data or instructions. The communication operations enable the PLC to interface with external input-output modules, other PLCs and external devices. The communication with the CPU is facilitated by the data bus and the address bus. Okay. Now the address bus, it activates specific input output points or memory locations which coordinates with the data bus for the data transmission. The microprocessor, however, selects an address which is decoded to choose the appropriate input output point or a specific location for the data transfer operation. The database is consisting of a bidirectional channels, allows the data to flow between the CPU, memory and the input-output modules. The key components of the microprocessor include the Arithmetic Logical Unit, also called as ALU. It performs the basic arithmetic and logical operations and also the program counter operation, which controls the sequence of program instructions. Here in this diagram you can see the typical parts of a microprocessor which is used in a PLC. Next, the internal registers store the data and instructions temporarily for the ALU or Arithmetic Logical Unit use. A clock ensures that all the operations are executed in a timely and also in a synchronized manner. The operating system, which is stored in read-only memory, ROM memory, is a permanent program that controls a microprocessor which is written in assembly language to perform the internal functions, control units and also handles the communication efficiently. The memory includes a read-only memory ROM for the operating system and executable program and random access memory RAM for the user's program and operational parameters. The operating system is also responsible for the execution of various diagnostic functions from the Central Processing Unit. The diagnostic functions are crucial for ensuring the proper operation of the PLC. The system initiated diagnostic performs during the device initialization. It checks the RAM, the random access memory, microprocessor battery and also checks the proper power supply. The users can also initiate the specific diagnostic tests which are related to the memory, the communication ports and other units through the diagnostic instructions in the user's program. This diagnostic process helps to maintain the programmable logic controller reliability and its functionality. Under this, let's talk about the memory organization. The memory of a programmable logic controller is organized into various sectors to store the executable program, the user's automation program, the input-output states and the non-permanent data. Here in the figure, you can see the usual organization of a memory in PLC, which are broadly classified in the ROM, the random access memory and the read-only memory. The memory organization basically involves segmenting the memory into different areas, each with a specific purpose and a specific size, which are tailored to the PLC size and capabilities. While memory sizes vary between a PLC with 128 input outputs but also one with a 1024 input outputs, the fundamental structure will remain consistent. The memory capacity is measured in digital bits. For instance, a 1 kilobyte of memory can store 1024 bytes, and translating it to either 1024 program instructions or 8192 discrete or input output states depending upon the usage and its application. The operating system, which is stored in the read-only memory, directs the microprocessor to perform tasks such as scanning the inputs, updating the outputs and also executing the user's program loaded. The automation program instructions, whether graphical or alphanumeric, are stored in the binary form in the automation program or either in the user program sector. The operating system mainly translates these instructions into assembly language and manages the data retrieval from memory as per need, such as fetching the input states from the input image table. When the scanning input state continues, the microprocessor stores the data in the input memory, mapping memory, and also the output states are similarly stored in the output mapping memory, and next the output states are transferred to the output modules after the automation program execution. Additionally, the central processing unit uses the specific random access memory sectors to temporarily store the data results and parameters which are related to the counters, timers and auxiliary functions. Here you can see the general internal structure of a PLC. The auxiliary memory, it bits in the PLC's function similarly to the auxiliary relays in the traditional automation circuits. This single bit memory location represent the operational states and are used in automation program instructions to mimic the relay contact. This setup allows for an infinite number of contacts within the program, with each bit having a unique address. Overall, the PLC operation involves defining the input addresses, transferring the input states to the memory, executing the program instructions, updating the output states and also referring to the internal units like the timers and the counters. The operating system in read-only memory control all these processes, while the programmable logic controller may be used as a battery to retain the random access memory contents during a power outage, and an additionally electrically erasable programmable read-only memory called as EEPROM memory for permanent program storage. This structured approach ensures that the PLC can manage complex automation tasks efficiently and reliably. Now let us talk about the memory types. In the programmable logic controllers, there are different types of memories are used, each having its specific functions and characteristics. They are read-only memory called as ROM, random access memory called as RAM, the erasable programmable read-only memory EPROM, the electrical erasable programmable read-only memory EEPROM, and next the flash memory. Now comes in detail with the read-only memory. Here the read-only memory is a non-volatile and permanently stored data and program that do not need to be modified. In a PLC, the ROM is primarily used to store the operating system, which contains the core instructions needed for the PLC proper operation. The ROM retains its data even when the power is lost. So it eliminates the need of any emergency power supply, because even when the power is lost, it will retain its data. Next is the random access memory called as the RAM. It is a read or write memory that only allows both data and program to be written and read repeatedly. It is very highly flexible and is commonly used for storing the user's automation program and other data which are generated during the program execution. But RAM is a volatile memory. It loses all its data when the power is lost. To mitigate this, the PLC often includes or uses a battery to maintain the RAM contents for about a year during power store to maintain and restore its RAM content. Next is the erasable programmable read-only memory called as EPROM. It is now largely outdated and replaced by the EEPROM called as electrically erasable programmable read-only memory. It is a type of ROM, read-only memory, that could be reprogrammed after being erased using an ultraviolet light. The EPROM retains its data during the power loss, but it requires removal from the PLC and an external erasing unit to update its content, making it less convenient to use. While on the other hand, the next type, which is called as EEPROM, the electrical erasable programmable read-only memory, can be erased and rewritten using the electric voltage, making it more flexible and more convenient than the EPROM or the erasable programmable read-only memory. The EEPROM does not lose its data during the power interruptions and can be easily updated without removing it from the PLC. While it offers similar flexibility to the random access memory RAM, but it is generally slower in accessing the data. Next and last is the flash memory. It is similar to the electrical erasable PROM, but is used in the many larger PLCs. It allows the block erasure of large data chunks rather than byte-to-byte erasure. Mainly it is suitable for storing the large programs or data. The flash memory is often used in conjunction with the electrical erasable programmable read-only memory EEPROM for extended storage capabilities. Additionally, some PLC can be equipped with external storage devices such as hard drives for storing the extensive automation programs or large data sets. This external storage expands the PLC capacity beyond its internal memory options. Each memory type serves as a distinct role in the PLC operation, from storing the critical system instructions and the user programs to handle the temporary data, and also allows the flexibility for the program updates. Now let's talk about the overview of PLC power supply. A PLC, programmable logic controller power supply, is very essential and very important unit for converting and supplying the electrical power to the various components of a PLC system. It ensures that the PLC, its input-output modules, the communication modules and the other components receive stable and appropriate voltage and current throughout its operation. Here you can see the structure of the central processing unit with the programming device, with the push button, the power supply and the output indicator, the light and the visual alarm. Next are the types of power supply. First is the AC power supply. Now the input voltage range of AC power supplies. The PLC typically use AC power supply with input voltages like 110 volt, 220 volt or 240 volt AC. The exact input voltage depends on the region and also on the specifications of the PLC. Now the output voltage range. The AC power supply converts the incoming AC voltage to a regulated DC voltage, commonly the 24 volt DC or 12 volt DC. This DC output powers the PLC and also its components. Now next is the DC power supply. Now the input voltage range of DC power supplies are used in a system where a DC input is required. They may accept various DC input voltages depending upon the application. Next is the output voltage. The output voltage range of DC power supply provide a stable DC voltage which are typically range from 24 volt DC, 12 volt DC or either 5 volt DC as required by the PLC system or depend upon the PLC application. Now integrated power supply. Some PLCs come with an integrated power supply, which means the PLC includes a built-in power supply unit. This simplifies the installation of PLC and also reduce the need of external components and make its installation and designing easy. Next is the external power supply. For modular or for large PLC system, an external power supply is often used. This allows the flexibility of selecting a power supply that meets the specific requirements and provides isolation from the PLC internal power needs. Next is the power supply specifications. Next is the voltage rating. Now the nominal voltage rating. The power supply must match with the PLC's voltage requirements precisely. The over voltage or under voltage can lead to system instability or damage of the complete system. Next is the tolerance. The power supplies usually have a tolerance range, for example, the plus minus 5% for the output voltage, which ensures the compatibility of power supply with the PLC's operating range to prevent the system instability or damage. Next is the current rating. Now the capacity of the current rating. The power supply must provide enough current to support the PLC operation and also to the all connected devices. The current rating is very crucial or important to avoid the overloading of the power supply and to prevent the damage of the system. Now the peak versus continuous power supply. Considering both in peak and the continuous current requirements, some systems must have temporary peak demands that can exceed the average current need. Now the power supply protection. First is the over voltage protection, which includes surge protection and the voltage clamping. Now the surge protection, it prevents damage from the voltage spikes or surges preventing the voltage line. The surge protectors or transient voltage suppressors called as TVS can be used for over voltage or for the surge protection. Next is the voltage clamping. The devices that clamp the voltage level to a safe level protect the PLCs from the high voltage transients and prevent it from further damaging of the system. Now next is the second is the overcurrent protection, which includes circuit breakers and the fuse. Circuit breakers, The circuit breakers automatically disconnect the power supply if the current value exceeds a set threshold or a safe current level, which protecting it against any overloading condition generated in the system. Next is the fuse. It provides a simple way to protect against the overcurrent condition by blowing and disconnecting the circuit in case of any excessive current condition. Now third is the short circuit protection, which includes internal fuses, current limiting. First, internal fuse. Many power supplies include the internal fuse that protect against the short circuit by disconnecting the circuit if a short circuit condition occurs in the system. Next is the current limiting. Now, some power supplies have the current limiting features that restrict the amount of current during a short circuit condition. Next is the power conditioning circuit, which includes voltage regulation and the filtering circuit. Now, the power regulation ensures that the output voltage remains stable despite the fluctuations in the input voltage or in any load condition. Next is the filtering circuit. The filtering circuit reduces the electrical noise and prevent any ripple in the output, and it ensures that the clean, neat and a very stable power supply for the sensitive PLC components to ensure the safety of the PLC. Now the installation and the operation of PLC, the programmable logic controllers. This installation and operation of PLC require very careful adherence to specific guidelines and standards to minimize the potential operational issues, particularly in challenging the industrial environments. The primary source of installation guidance should always be the PLC manufacturer's instructions, which provides the tailored advice for each PLC module. Under this, let's talk about the electrical enclosure for PLC installation. In industrial electrical enclosures must meet international standards that ensure appropriate protection for both the equipment and personnel. For instance, the National Electrical Manufacturers Association, called as NEMA, specifies the enclosure type 12 for electronic control devices, which provides the protection against access to the hazardous parts and guard the person against the solid foreign objects like the dust and lint, as well as light water splashes. Similarly, the International Protecting Rating, the IP rating system, defines various levels of enclosure protection, with codes indicating how well an enclosure resists the dust, water and other environment factors which are present. These ratings are very crucial for selecting the right enclosure based on the specific conditions where the PLC will operate. Now the heat dissipation. The proper heat management is very critical in PLC installation. The temperature inside the electrical enclosure should never exceed the PLC's maximum operating temperature, which is typically around the 50 degrees Celsius. The adequate enclosure size and ventilation must be ensured to handle the thermal load generated by the PLC operation and any additional power devices installed. This may involve calculating the required dimensions and also accessing the need for ventilation to maintain a safe operating temperature. Now next is the electromagnetic interference, called as EMI. To prevent the electromagnetic interference from affecting the PLC operation, it is essential to separate the high power electrical equipment from low power electronic or control devices within the enclosure. The high power equipment includes the components such as power relays, transformers, frequency converters and the DC power supplies. The proper segregation helps and also ensures that EMI, the electromagnetic interference, does not disturb or disrupt the PLC performance or reliability. Next, when installing the PLCs and other low power control equipment, it is very crucial to manage the electromagnetic interference and also the galvanic coupling to ensure the reliable and safe operation. The low power control equipment includes the PLC itself and other specialized electronic devices such as electronic stepper motor drive cards. Now next is the galvanic coupling and the interference. The galvanic coupling occurs when two or more electrical circuits share a common conductor between them, which can lead to the interference between the circuits. For example, in a typical setup where a relay is energized, a voltage drop in the shared conductor can affect the PLC signal. This is clearly illustrated in a figure A, where the impedance Z in the common conductor causes the unwanted voltage drop that interfere with the PLC operation. Now next is minimizing the interference. To minimize the interference caused by galvanic coupling, it is essential to reduce the length of the common conductor shared by the high power and the low power circuits. Shortening this common path helps to decrease the interference effects due to the voltage drop. In the figure B illustrates this concept, showing how a short common conductor can remove the impact of voltage drop on sensitive control equipment and can minimize the interference. Now let us talk about the grounding. Proper grounding is very essential for the reliable and the safe operation of industrial installation, which involves a PLC, the programmable logic controller. The inadequate grounding can lead to issues that are difficult to diagnose, as problems may be incorrectly attributed to software or hardware fault. This misdiagnosis can result in engineers spending the unnecessary time troubleshooting the programming issues when the real problem lies with the hardware grounding. Additionally, the inadequate and the poor grounding can affect both the functionality of the PLC and also the safety of the personnel, as it often contributes to electrical noise and the interference. To avoid these grounding problems, it is very crucial to follow the specific grounding guidelines. First step, the PLCs should be grounded accordingly to the manufacturer specifications with all the grounding conditions made securely using the screws. Second, the evaluate enclosure grounding means check that the electrical enclosure housing the PLC is very popular and adequate grounded. Next, third is the resistance requirements. Ground conductors should have resistance below the 0.1 ohms, which includes the connection between the earth bus bar and the ground. Fourth step is to ensure the continuous grounding. The grounding change must be uninterrupted from the ground electrode to the PLC and its components to avoid the partial grounding. Fifth point is to consider the lightning protection. Proper grounding is especially important or very important if the system includes the lightning protection in its enclosure. Next, talk about the electromagnetic shielding of cables. The electromagnetic shielding of cables is crucial for protecting the low voltage signals such as analog measurements and data from the interference. Shielding can take various forms, which includes the metallic enclosures or specific cable shielding techniques. The primary goal is to block the electromagnetic interference between the adjacent cables by either reflecting or conducting the electromagnetic interference to the proper ground. Here in the figure you can see the grounding of a shielded cable connecting an analog sensor to a PLC. The common types of shielding includes foil shields, which uses a thin layer of aluminum, braid shields made of woven tinned copper, double shields which combine foil and braid for enhanced protection, and triple sheets which include foil, braid, foil connection for extremely noisy environments. The effective shielding depends on the impedance of the mesh and its frequency characteristics. The lower impedance generally removes the shielding effectiveness, which allows the mesh to handle the large discharge currents. For low frequency magnetic fields, generally twisting semiconductors can also be effective and can be used. The data cables and analog signal cables should always be shielded with specific grounding practices, like analog cables should have their shielding grounded at only one end, which is near to the PLC, to prevent the ground loops, while data transmission cables should have their shielding at both the ends to protect against the high frequency interference. Importantly, the shielding mesh should never be used as an equipotential bonding conductor. So that's all for today's lecture. In this lecture, we have covered the fundamentals of programmable logic controller, and under this we have covered the PLC central processing unit and the power supply. In the next session, we will explore more deep in the PLC and will discuss about the PLC programming part. So thank you. Have a nice day.